Good morning, it's Mr. Craich. Today we're going to talk about centripetal force, which means center-seeking force, and it's a motion caused or a force caused by motion in a circle. So whenever you're moving in a circle, you'll feel some sort of force on you, and that is called centripetal force. So good morning, let's get going. A typical playground ride that you may have been on at some time, called the merry-go-round. It involves centripetal force. You move in a circle and you feel a force, and you can see that girl has to really hang on the faster she goes. So she has to hold on with centripetal force or she'd go flying off the ride. Is the Gravitron type of rides. They basically pin you against the back of the ride and you feel a force on your back holding you into the middle of the circle. And that's the centripetal force that you're feeling. So centripetal force just means center seeking, so centra and pedal towards the middle, seeking. And basically we call centripetal force F-cent, or sometimes they call it FC, and it's just caused by moving in a circular motion. Usually, just to keep the math simple, it's at a constant speed. So we'll always say that it's at a constant speed, moving in a circle. Newton's second law says F equals ma. So if there's a centripetal force, there has to be a centripetal acceleration. So if you're moving in circles, you must be feeling some centripetal acceleration, which are often called g's. So that m would be your mass in kilograms, a would be meters per second squared, of course, and your centripetal force would be measured in newtons. Just filling in the units, we've got newtons, kilograms, and meters per second squared. When we're talking about amusement park rides or merry-go-rounds, for instance, that m, the mass, would be your mass. The acceleration would be the centripetal acceleration you'd feel. And then obviously the F-cent would be the centripetal force that you feel. In this picture, I've tried to draw a merry-go-round, circular merry-go-round, going at constant speed. This is the top view, and basically we've got a radius right here from the center to the outside. So that would be a radius, or this would be the same radius, same here and same here. On a merry-go-round, these are the bars that you hang on to so that you don't fall off as it spins around. This merry-go-round, we've got top view, and basically at one point in time you're at point A, another point in time you've moved and you're at point B. So I'll call the velocity here V initial, and I'll call the velocity here that you would have V final. They're actually vectors. Velocity depends on not just the amount, but also the direction. The amount's the same, so the length of these speeds are the same. So the length of the velocity vector is an indication of the speed. The speed is just the magnitude part, the number part of the velocity. But what's changed is the direction. So the speed is the same, the length of those arrows is the same, but the direction has changed. And that's crucial because that will show you how you get an acceleration from something that's going at a constant speed. According to the kinematics that we learned even back in grade 11, acceleration is due to some change in velocity over a change in time. So if we could have a change in velocity, we would have an acceleration. And like I say, the speed part doesn't change, but it's the direction of the velocity that does change. So we'll prove right now how we can get a centripetal acceleration. Remember, the change in velocity is just the final velocity minus the initial velocity. And that's the same with anything. The change in anything is always the final minus the initial. But we have to remember that velocity is a vector. We have to figure in the direction as well. So if I was to go velocity final, it's in that direction. So I've got velocity final, and minus this vector means like adding that vector in the opposite direction. So I have to add VI, but in that direction. So I've got VF and this one here is minus VI. It's VI, but in the opposite direction. So I get a situation that looks like this. I've got VF in that direction, and I add VI negative in that direction, and I end up having a resultant vector that's going in this direction. That is the change in velocity vector. So if I was to put in all the other numbers, this is VF, this is minus VI right here. Get rid of that. And that's my change in velocity vector. So at a point between A and B, that change in velocity vector is pointing right towards the center of the circle. So my change in velocity vector right between A and B is pointing in that direction right here. That's the change in velocity vector, pointing right towards the middle of the circle. If the change in velocity vector is pointing in towards the middle of the circle, A, which is the centripetal acceleration, is directly proportional to V, which means that if V is pointing in that direction, A has to point in that direction too. So the centripetal acceleration is also pointing dead on right into the middle of the circle. So one more time, if change in velocity is pointing towards the middle of the circle, the acceleration has to point towards the middle of the circle too. And that's why they call it centripetal acceleration. Just to fill in the rest of the details that might have been missed at the bottom of the board, change in velocity is VF plus VI in the opposite direction. So the change in velocity is pointing that way and right in to the middle of the circle when you're at a point directly halfway between A and B. And if the change in velocity vector is pointing towards the middle, then the acceleration has to point directly towards the middle of the circle too. So if the change in velocity vector points towards the middle, then the centripetal acceleration points towards the middle, because A centripetal is change in velocity over change in time. And F centripetal also points towards the middle, because F centripetal is equal to M times A centripetal. So because F equals MA, F has to point in the same direction as A, and because A equals change in velocity over change in time, it points in the same direction as the change in velocity. So always towards the center. Just getting into a bit of the math here. A centripetal has a formula. It's the V squared divided by R. So the speed that it's traveling at in a circular motion divided by the radius of the circle. For the sake of Physics 11 and Physics 12, we'll keep this V a constant speed. So that number will never change. The units, V would be a speed in meters per second, R would be the radius in meters, and centripetal acceleration, of course, would be in meters per second squared. Just note that you could get the V by using a radar gun of someone on a ride, or you could get that speed by just measuring the circumference that they go around in their circle, divided by period, which is the amount of time that it takes to go around that circle. So the distance around the circle divided by the time it takes to go around that distance. That would be 2 pi r, the circumference, divided by t, the period. And that would be your speed of that circular motion that you're going in. Speed, which is 2 pi r over t, into this formula here, I get A centripetal is equal to V squared, which is 2 pi r over t squared divided by r. And just to simplify, make it a little bit more digestible in terms of putting numbers in, I get 2 pi r over t squared over r over 1, and that equals 4 pi squared r squared over t squared. all over r over 1. And that becomes four pi squared r squared over t squared times 1 over r. And that can simplify to something a little bit more digestible, like I said. One of those r's is gone, that one's gone, and I just end up getting 4 pi squared r over t squared. So the other usable formula for centripetal acceleration is 4 pi squared r over t squared. And you'd use that whenever you're given the period, for instance, the amount of time it takes to go around the whole circle. So you have two versions of centripetal acceleration, v squared over r, or 4 pi squared r over t squared. And then, no surprise, to get F centripetal, you just go F cent is equal to m times a centripetal. So no surprise, centripetal force could be m4 pi or m v squared over r, or m 4 pi squared r over t squared. You just put the m in front of it. So again, centripetal force is mv squared over r, or m 4 pi squared r over t squared. So in your spare time, get out and find a merry-go-round. Somewhere in town, there may be one. I know they're starting to be farther and farther between locations to find, but they are coming out with new ones too. They're quite a bit smaller than the old ones, and they might only hold 2 kids, but they are merry-go-rounds. Try the Gravitron or a ride like that at Playland or some other amusement park. And maybe try vertical centripetal forces, like go in a ride that has a vertical loop. And we've got some even at local playground or local amusement parks that come to town that fire you in a loop and you just keep going around and around and around. But there are also looping roller coasters as close as West Edmonton Mall that are really cool. You get to feel lots of G-forces, and it's all because of centripetal force. Okay, take care. See ya. Bye.